All right, welcome to another IAEI News Live. My name is Thomas Dimitrovich, and today we're going to continue our discussion on the real-world example that we talked about last week and the week before. Remember last week we focused on the transformer. Today we're going to focus on the tap conductors, and it all starts now. All right, welcome back. So, before we get started, I just want to say that remember the IAEI section meetings are going on right now. And that is, I believe we got through the Western section, Northwestern, Southwestern, Eastern section, just finished up this past week. So again, if you missed the section meetings this year, consider the section meetings for next year, because they present a unique opportunity to meet those who are directly involved with the development of the National Electrical Code and other NFPA as well as standards development activities. It's an opportunity to build your network of influence and your networking for resources to help you answer questions and any of those areas where you just want to bounce something off of someone who might be either sitting on a code making panel involved with that standard for the specific product that you're looking at, or whatever it is, just in general electrical knowledge. So great opportunity that the IAEI presents. Please, again, get out there, check on the section meetings. This is a recorded session. Just want to say that right off the bat. This is a recorded session. And we're going to dig into taps and tapped conductors. So hopefully you got your National Electrical Code out. We'll be referencing, I'll probably be looking at the 2023 NEC, which I don't know that a lot has changed in regard to the tap rules. And we'll also take a look at transformer secondary conductor rules too. So let's get into it. And if you remember, this was the application that we were dealing with. You'll notice that, again, this is a not service equipment. So that's there's a couple unique things about this application. One is it looks like a service. It looks like what you might see on the outside of a building that would be treated as a service because the utility would be connecting, but this is not a service. This basically over here on the left-hand side, that's a feeder. Remember, this is just a disconnect. This is, there is no fuse inside that disconnect. There's a transformer, and then you have a secondary main overcurrent protective device, which is a fusible disconnect switch. And then you move into a trough, and those are taps that are serving the loads through those switches. Now, another thing that I really like about this application is it is a tale of the times. If you look at just the equipment, just look at the equipment that is in this application. This is what we got. We have one manufacturer's disconnect switch on the primary of this transformer. We have a different manufacturer's transformer. We have yet a third manufacturer's fusible disconnect switch on the secondary of that transformer, and then yet a fourth manufacturer of the disconnect switches that are going to each of the units that this is serving. And the reason I say it's a tale of the times is because today, as you know even more so than I do, it's harder to get equipment than it was a year or more ago. I would say pre-COVID. So the challenges of just getting equipment are being solved by this type of engineering, so to speak, putting together a system that is comprised of multiple manufacturers. It's just a tale of the times. So All right, so what I want to do is I want to focus on this here. This is where you would have your taps. And the conductor length, the conductor from that go up to this switch would be your tap conductor, and the reason this is a tap conductor, and it's not a transformer secondary conductor. This is a transformer secondary conductor, which serves an overcurrent protective device, OCPD, which protects a feeder, right? So there's a feeder, and then off of the feeder are tapped conductors. So these are feeder taps. This is your transformer secondary conductor, and there are requirements around that, and I want to take a look at that too, because that's in Article 240 as well. So get out your code book. And in Article 240, we'll walk through the requirements. So now, here, I'll show you this too. So now, this is a look inside of the trough. And you'll notice these are the conductors that are coming from the secondary of that transformer. And this is a power distribution block. Those are where your taps are taking off of. And you'll notice that the tapped conductors go out and they go up. There's two per raceway going into the switch, because these switches, there's your two coming in, and there's your gazintas and your gazaltas. So you got two coming into the switch and two leaving the switch, and you have two fuses because this is a single phase application. So that's basically what you got going on. And what we're going to talk about are the rules around those tap conductors. We'll also talk about the rules around that transformer secondary conductor. All right, so the first thing that I want to do is, all right, tap conductors, right? 240.21 in the National Electrical Code talks about, remember, 240 is overcurrent protection. 240.21 tells you the location in the circuit for overcurrent protection. It's separated into 8, I guess, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, H is 8. 8 different first level subdivisions. You have your branch circuit conductors. This is where we're going to be focused. Feeder taps, that's one area that we're going to be focused on. And then transformer secondary conductors. Because obviously we have transformer secondary conductors, and then we have feeder taps. We don't have to worry about service conductors because this isn't service equipment. I don't have to worry about busway taps because this isn't busway. It's obviously not a motor circuit, and there's no generator involved, and we got no battery involved. So we're going to focus on feeder taps, 240.21b and 240.21c is in Charlie for transformer secondary conductors. All right. So what does 240.21 tell us? Remember that we have to protect a conductor at its ampacity. So the location of the overcurrent protective device ahead of any conductor is what protects the conductor from two things. One is an overload. And remember, an overload is when all of the current stays in the path. And then a short circuit is when the fault current goes outside of the normal path. So the overcurrent protection, which is at the beginning of a branch circuit or a feeder, that overcurrent protection protects that conductor at its ampacity for overloads and short circuits. Okay, so overcurrent protection is required for every ungrounded circuit conductor. And the overcurrent protective device has to originate where the conductors receive their supply. Okay? Now, the tap rules that's basically what's going on in this application. You've got a scenario where You do not have for the conductor that's on the secondary of those power distribution blocks. It's on the secondary of the power distribution blocks. So we have one size conductor coming in here, and we have a smaller conductor going out, but we don't have overcurrent protection at the beginning of that conductor. So it's not being protected at its ampacity. So what 240.21 tells us is that if you don't have overcurrent protection at the beginning of that conductor, you need to follow the rules in 240.21a through h. And that's going to rely on you and I determining whether or not it's a feeder tap. These are transformer secondary conductors. If they're service conductors, busway taps, motor circuit taps. So you've got to look at the application and figure out which of these sections you are in. And then follow those rules. And then realize, and you've probably heard this before, you can't tap a tap, right? So if a conductor is supplied per 240.21a through h, then you cannot supply another conductor except through an overcurrent protective device meeting the requirements of 240.4. So you can't tap a tap. You can only tap a feeder one time, period. Or transformer secondary conductors, any of these in A through H, you can only tap them once. All right, so let's take a look at feeder taps because we've determined, okay, let's take a look at our diagram. We will have determined, we've determined that if you just look at this draw, let's take a look at the drawing here. Remember I did this diagram. So there's our transformer right here. There's our transformer secondary conductors right there. And then we have our fusible disconnect switch right here. That tells you that because I have an overcurrent protective device there, the conductors on the secondary of that overcurrent device is protecting that conductor at its source. So that is a feeder. Those aren't tap conductors. You no longer consider the conductor that's in that trough. You no longer consider it a transformer secondary conductor because the transformer secondary conductors are from the transformer secondary, which is not protected by an overcurrent protected device at its source. And then it lands on a switch, fusible disconnect switch. So that is a transformer secondary conductor right here. That is your transformer secondary conductor. Let's highlight that in yellow. Okay, those are your transformer secondary conductors. Okay, let's just get rid of all of this. I'm going to separate all of that. Just get out of my way. All right. Okay, so this conductor right here in yellow is a transformer secondary conductor. The conductors in this trough in yellow here, this is a feeder because it's protected at its source right here. There's an OCPD, an overcurrent protected device, a fuse in that fusible disconnect switch. So the conductors that originate at the secondary of that, or at that fuse and beyond, that is a feeder. And then we go to a smaller conductor up to these switches. And I believe those are number 2s, 2 American wire gauge, if I'm not mistaken. Those are number 2s, and we've determined, now, if you recall, so let's go back down through all of our math. Remember this discussion from last week. We went and we calculated the primary and secondary full load amps. We calculated the secondary fault current. We calculated the primary overcurrent device. And we calculated the secondary overcurrent protective device. And we said that this could be as high as a 300 amp overcurrent protective device. And that's going to be important when we start talking about the maximum size of our tap conductors, because there'll be a percentage of our overcurrent device which is protecting the feeder. All right, so we got to keep that in mind, 300 amps. Okay, so let's go back down through this. There's our two, our number, these are all number twos. And when we said we're going to make that a 250 amp OCPD, because our maximum is 300, but we're going to make it a 250 amp OCPD. Actually, this installation had a 400 amp overcurrent device in that switch, which was obviously ungood. So to fix that problem, they either have to lower that overcurrent protective device to something 300 amps or less, or change the feeder size to match a 400 amp worth of ampacity. Or, I mean, the transformer will only let you do so much as well, right? So I can't put 400, I have to put 300s. I could maybe split that up into two different discussion. All right, so now let's take a look at our rules. The feeder taps. So B says conductors are permitted to be tapped, which means there's no overcurrent protection at its source. We already established that. The tap is permitted at any point on the load side of the feeder overcurrent protective device. And 240.4b is not permitted for tap conductors. So you can't, remember 240.4b lets you upsize the overcurrent device from the ampacity of the conductor. So you're not allowed to do that with 240.4b. All right, so there are 5 conditions here. You have taps not over 10 foot, taps not over 25 foot, taps supplying a transformer primary plus secondary not over 25 foot long, and then taps over 25 foot, and then you have outside taps of unlimited length. Now, I'm just going to bring up, so the first thing, actually, the first thing we got to do is we've got to figure out what's the length of these conductors. So if we go back to the picture, I don't have the measurements on this, but here's what we do know. A brick is just about 2.5 inches tall. So if I think I got to come down I have to come down 1, 2, 3, and then I got to come over, which we'll not count that yet. And then I got to come back up, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's just to the equipment. So if we said, say 16 times 2.5 inches, we're at 40 inches, right? So if we go back to our presentation, that's 40 inches. 40 inches divided by 12. That's 3.5 foot. So if I look at my example, that's 3.5 foot plus some slop this way, plus a little bit length in there, plus a little length in there. I'm not going to exceed 10 foot. So I'm going to look at the requirements for taps not over 10 foot long. And if we look at the NEC, which I'm looking at the 2023 edition of the code, taps not over 10 foot long. So what it says is if the length of the tap conductors do not exceed 10 foot and the tap conductors comply with all of the following, right? So the ampacity of the tap conductors, not less than the combined calculated loads of the circuits supplied by the tap conductors, and that's a load calculation, which I'm not including in this discussion. I'm going to assume if that installation, and we all know what happens when you assume, but for argument's sake, I'm going to say that they did the right calculation, and a number 2 is going to be fine. not less than the rating of the equipment containing an overcurrent device supplied by the tap conductors. So if that's a number 2, number 2, then my ampacity, these switches, which I believe these are 100 amp switches, if I'm not mistaken. I think so. Let's double check. Yep, those are 100 amp switches. So I can't. So those the number 2s have to land on an overcurrent device which is at that ampacity. The tap conductors do not extend beyond the switchboard, switchgear, panel board, disconnecting means, or control devices they supply. So all of it is contained inside of that enclosure because it lands on an overcurrent protective device. And the moment it lands on an overcurrent protective device, you're moving from a tap conductor to a feeder. So that length of conductor does not go beyond the equipment, so we're good there. Except at the point of connection to the feeder, which is that device. The tap conductors are enclosed in a raceway, which extends from the tap to the enclosure of an enclosed switchboard, switchgear, panel board, or control devices, or to the back of an open switchboard. So this raceway is enclosing the tapped conductors that go into that switch enclosure, so everything is contained. Because remember, if you got to remember that those conductors are not protected at their ampacity. So you got to be mindful that the conductor has to be protected, just like service conductors. We protect service conductors, right? We go to to the nth degree to ensure the protection of those service conductors. Why? Because it's very similar to this. They come out of that system, they come out of the application, they're not protected at its source, so we have to put protection around it. And we're doing the same thing here. And then finally, for field installations, if the tap conductors leave the enclosure or vault in which the tap is made, the ampacity of the tap conductors is not less than 1/10 of the rating of the overcurrent device protecting the feeder conductors. Now, for field installations, if the tap conductors leave the enclosure, now you have to look at this application and say, do we leave the enclosure, right? And I could make an argument that we do not leave the enclosure. I mean, if you look at everything, the tap conductors are all enclosed, so I would make an argument that we're not leaving the enclosure. All right. All right, so let's just follow this through. Okay, so we've met all the requirements for a feeder tap. All 4 conditions are met. And we've covered the rules around those tapped conductors. Now, let's talk a little bit about transformer secondary conductors. Okay, so this is in 240.21c, Charlie, transformer secondary conductors. That would be, again, if we go back to our image, the conductors that are in that raceway are our transformer secondary conductors. There's no overcurrent protective device at the source of that conductor. So it's not being protected at its ampacity because the protection of that conductor is really only achieved by what's on the primary of the transformer. And if you think about how we size, and remember, that's just a disconnect switch, there's no fuse in there, but there's a circuit breaker that is feeding that switch. That disconnect is just there to help the electrical contractor, electricians establish an electrically safe work condition, right? To turn that transformer off for maintenance and other reasons. So that line side overcurrent protective device in the transformer, let's draw it out. So what you've got there is we have a circuit breaker feeding a disconnect, feeding a transformer, which then goes to a fusible disconnect, and then to our taps, right? So this right here, that portion of the circuit, is our transformer secondary conductors. I forgot the N. Secondary conductors. The protection of those conductors, right? There's no overcurrent device at its source. The only thing that could possibly give you any protection is the circuit breaker that's on the primary of the transformer. And that device is selected for inrush. We have to make sure that the transformer can be energized. And the only way to do that is to make sure that the instantaneous pickup of that circuit breaker, we want to make sure that this region of that circuit breaker is not detected by the inrush current for that transformer, and thus tripping that primary overcurrent protective device. So it's inflated in size to handle the inrush. So it is definitely not going to protect those transformer secondary conductors. And if we look at our rules, it says in 240.21c, transformer secondary conductors, a set of conductors feeding a single load or each set of conductors feeding separate loads shall be permitted to be connected to a transformer secondary without overcurrent protection at the secondary, as specified in 240.21 Charlie 1 through Charlie 6. Section 240.4b shall not be permitted. Remember, 240.4b, let's just go up and I'm just going to take a look and read that to you. 240.4b tells us that the next higher standard overcurrent device above the ampacity of the conductors being protected is permitted to be used provided all the following conditions are met, and this is for 800 amps and less overcurrent protected devices. The conductors being protected are not part of a branch circuit supplying more than one receptacle. The ampacity of the conductors does not correspond with the standard ampere rating of a fuse or circuit breaker, etc. And the next higher standard rating selected does not exceed 800 amps. So if you meet that criteria, then you can go to the next level higher than the ampacity of the conductor. But in the case of transformer secondary conductors, you can't do that. In the case of tap conductors, you cannot do that. So back in 240.21c, we begin with that sort of the ground rules, and then the parent text of 240.21c says, look, you can install a conductor on the secondary of a transformer. You can install a conductor on the secondary of a transformer as long as you follow the rules found in 240.21c 1, 2, 3, 4, 5, or 6, right? So there's your 240.21c, and then you have 1, 2, 3, 4, 5, or 6. Now 1 gives you that unique, and this is where a lot of people, a lot of engineers and designers will miss this one. For you to claim that The primary overcurrent protective device offers protection of the secondary conductors. You have to meet 240.21 Charlie 1, which states the conductors supplied by the secondary side of a single-phase transformer, single phase, not what we have, having a 2-wire secondary or a 3-phase delta-delta connected transformer. So there's the second condition. If it's a 3-phase delta-delta connection transformer having a 3-wire secondary, are permitted to be protected by the primary overcurrent protective device on the primary of the transformer, provided that you are in accordance with 450.3 and doesn't exceed the value, which we could take a look at 450.3, determined by multiplying the secondary conductor ampacity by the secondary to primary transformer voltage ratio. So what you're doing is you're transposing. You're taking the secondary amp rating of the conductor on the secondary of the transformer, multiplying that by the secondary voltage, dividing that by the primary voltage. So you're transposing the ampacity of that conductor to the primary, and then comparing that with the primary overcurrent protective device. And that's only for two types of transformers, two types of systems. One's a single phase, 2-wire, and the other is a delta-delta. So for those cases where you have delta-Y ground transformers, which is probably the bulk of what we deal with, you're not going to get away with establishing the primary overcurrent protective device protecting the secondary conductor because of that rule, 240.21 Charlie 1. Now, so that tells you that that secondary is going to have to be restricted by length. It's going to have to follow the rules of 2, 3, 4, 5, or 6. Now, 2, and you're going to see this is similar to the tap rules that we just looked at for feeders. You have, when your secondary conductors are not over 10 foot long, when your secondary conductors are not over 25 foot long, when they're an outside secondary conductors, which this transformer is outside, right? So the transformer, based on the image, it's an outside transformer. The conductors, the raceway, all of that stuff is all on the outside. So you could be looking at 240.21 Charlie 4. And then you have secondary conductors from a feeder tapped transformer, which is not what we have. And then secondary conductors not over 25 feet long. And then item 3 is industrial installations, secondary conductors. So they treat industrials a little different than your, say, commercial buildings. All right, so if we take a look at the application again, all right, so let's take a look at, so we know this is an outside application just from the image, right? So let's take a look at the requirements. And again, we're talking about transformer secondary conductors. Let's take a look at the requirements in 240.21 Charlie, where's it at? Outside conductors 4. So it says, just going to get rid of all my marks. All right, it says, where the conductors are located outside of a building or structure, except at the point of load termination, and comply with all of the following conditions. I would say, so far, this application is definitely, and I think I have a further away picture. Yes, this application is definitely outside, right? So we can definitely say that we're so far meeting 4. But it says it has to comply with all of the following. 1, the conductors are protected from physical damage. Can you do me a favor? Can you plug me in? Are protected from physical damage. I gotta plug in my computer because I'm on low battery. This is what you get when you are live. Well, we're recording it, but we're pretending like we're live. So, all right, there we go. Thank you. All right, so we're outside conductors. Where the conductors are located outside of a building or structure, except at the point of load termination, and comply with all of the following conditions. 1, the conductors are protected from physical damage in an approved manner. So what do you guys think? I mean, we've got the transformer secondary conductors. They are in a raceway. They're very well protected. I would argue we meet condition number 1. The conductors terminate at a single circuit breaker or a single set of fuses that limit the load to the ampacity of the conductors. So we said this was going to be a 250 amps worth of conductor. As long as my ampacity of that transformer secondary conductors equate to 250 amps, not less, then I am meeting, we'll put 250 here. 250 amp fuse, OCPD, and 250 amps worth of conductor. So the conductors terminate at a single circuit breaker or a single set of fuses, so we meet that. The overcurrent device for the conductors is an integral part of a disconnecting means or shall be located immediately adjacent thereto. This is a fusible disconnect switch. Those fuses are an integral part of that switch. We meet condition 3. And then finally, condition 4, cross your fingers. The disconnecting means for the conductors is installed at a readily accessible location complying with one of the following. Outside of a building or structure, we're definitely outside. So we meet that one, but let's take a look at the other 2. B is inside nearest the point of entrance of conductors. We don't have to worry about that because we're outside. And C, it says where installed in accordance with 230.6 nearest the point of entrance of the conductors, and we don't have to worry about that one either. So since we're outside conductors, there's no length limitation. That secondary fusible disconnect switch did not have to be directly next to the transformer. It could have been down the ways because it's all outside. So we meet the requirements of the outside secondary conductors. Now let's take a look at the other requirements. If those transformer conductors did not meet the outside requirements, now we're inside the structure. Now I'm into the different rules. So 240.21 Charlie 2 says transformer secondary conductors not over 10 foot long. Now, what you see with these, remember, these transformer secondary conductors are not protected at its source. We already know that the only way the primary overcurrent device can protect those conductors is if you have a delta-delta transformer, if you have a single phase 2-wire transformer, and if you transpose that conductor ampacity to the primary and the primary overcurrent device protects that conductor, which is not the case in most of the applications that we install. So that secondary conductor is not protected. Very similar to service overcurrent protective devices. And we have a lot of rules to protect the service overcurrent protective devices, including the raceway that it's put in, the bonding, etc. You have similar rules for these transformer secondary conductors because it's very similar to that application. So for a 10-foot long run, if the length of the secondary conductor does not exceed 10 foot and complies with all of the following, the ampacity of the secondary conductors is not less than the calculated loads on the circuit supplied by the secondary conductors, and that's a load calculation, which, remember, we had a similar requirements for the tap conductors, because again, those tap conductors aren't protected at their source. So you have unprotected conductors, and you have to treat them special. So same thing for these transformer secondary conductors. Those conductors cannot be less than the rating of the equipment contained containing an overcurrent device supplied by the secondary conductors. So if this was a 250 amp disconnect switch, fusible disconnect switch, or 300 amps, whatever we selected, remember we can go as high as 300 amps, then the ampacity of that conductor cannot be less than that rating of those overcurrent protective devices and that equipment. Not less than the rating of the equipment containing an overcurrent device supplied by the secondary conductors, or not less than the rating of the overcurrent protective device at the termination. So if you didn't have that language, and if that was a 400 amp fusible disconnect and you put 300 amp fuses in, then that conductor size would have to be 400 amps. But because you have the or not less than the rating of the overcurrent protective device, which in this case could be a 250 amp fuse, then I can use 250 amps worth of conductor, and that 250 amp fuse could be in a 400 amp fusible disconnect. So exception where listed equipment such as surge protective devices, so they give you the exception for having a surge protective device in that application. Now, the second criteria, and it has all of the following. So you got to meet number one, you got to meet number two. The secondary conductors do not extend beyond the switchboard, switchgear, panel board, disconnecting means, or control devices that they supply. So that secondary conductor can't go beyond that secondary equipment. And the secondary conductors are enclosed in a raceway, which these are, which shall extend from the transformer to the enclosure of the enclosed switchboard, switchgear, panel board, etc. And then finally, for field installations where the secondary conductors leave the enclosure or vault in which the supply connection is made, the secondary conductors shall have an ampacity that is not less than the value of the primary to secondary voltage ratio multiplied by 1/10 of the rating of the overcurrent device protecting the primary of the transformer. So again, if it extends beyond, if you're not providing all that physical protection, then they want that overcurrent protective device that's on the primary to be of no more than a certain size as a ratio for that secondary conductor. So far, what we've talked about, that the fact that this is not service equipment, right? So this is not service equipment. So this conductor on that secondary that's leaving that switch, that fusible switch, this is a feeder, right? It's not a transformer secondary conductor. Why? Because I have an overcurrent protective device in that fusible disconnect switch. The conductors that are in this raceway here, those are taps, and the tap only extends from the gutter to the fuse. And if this was indoors and not external, because we got some forgiveness for external, because it's external to the building. I don't have to worry about causing a fire inside the structure. I am outside of the structure, and I just don't have to worry about I don't have to worry about those the combustibles, etc. So, and it's all enclosed in raceway. So I am following the tap rules for those outside of the conductors. But if I was inside, then I'd have to provide additional protection. And then I have to look at what are my requirements, right? So if, for example, I was dealing with where is it at? The feeders, I'd have to determine, how long is it? Am I greater than 10 foot? If I'm not greater than 10 foot, then I have to follow the rules in 240.21b1. If I am greater than 10 foot, but not greater than 25 foot, these are taps, then I'm in 240.21b2. Let's take a look at 240.21b2. What does that say? Now, these are, your feeder taps, and these aren't transformer secondary conductors. So now, if I go up to 25, so we saw the requirements of 10 foot, and if you don't remember what those were, rewind the video, go take a look at it. I'm not going to review it again, but let's take a look at the taps not over 25 foot long. Now we've extended a little bit further than 10 foot. And what am I doing? When I extend further than 10 foot, in between 10 and 25 feet, I've increased my exposure, right? If you think about risk, likelihood, and severity, I have increased the amount of exposure that I have, increasing the likelihood possibility of having a damaged conductor. So now, where the length of the tap conductor doesn't exceed 25 foot, then I have three conditions I need to meet. All three conditions. One, the ampacity of the conductors is not less than 1/3 of the rating of the overcurrent device protecting the feeder conductors. Now I'm worried. Remember, at 10 foot, all I was worried about was the ampacity of the conductor to serve the load. And then I couldn't be less than the rating of the equipment I was terminating in. When I get to 25 feet, now I'm worried about the ratio. Now I'm worried about that feeder overcurrent protective device, which is artificially greater. And I want to be within 1/3 of the rating of that overcurrent protective device. Because now I've increased my exposure, and now I want to make sure that my feeder overcurrent protective device, which, although it's inflated, I can still get short circuit protection out of that device. The ampacity of the tap conductor is not less than 1/3 of the rating of the overcurrent device protecting the feeder conductors. And then the second thing is the tap conductors terminate in a single circuit breaker or a single set of fuses that limit the load to the ampacity of the tap conductors, which we already had in the previous. The device shall be permitted to supply any number of additional overcurrent devices on its load side. And then 3, the tap conductors are protected from physical damage by being enclosed in an approved raceway or by other approved means. So what we don't see when I'm within 10 foot, I actually had permission for the conductors to leave the enclosure, the tap conductors to leave the enclosure or vault. But I don't have that provision here. Right. So, and remember, they said if it was not greater than 10 foot, they had the additional requirements that said, okay, now you have to think about 1/10 of the rating of the overcurrent device, etc. But they eliminated that. They built that into the first condition, which is 1/3 of the rating of the overcurrent protected device protecting that feeder. And then I still have to land on a set of fuses, right? And I still have to protect all of those from damage. So I only have 3 conditions that I can meet, which takes another option off the table for you. And then if you are over 25 foot long, now you have a list, 9 items that you need to follow. If we're over 25 foot long, it says where the feeder is in a high bay manufacturing building over 35 feet high at walls and the installation complies with all of the following conditions. So right off the bat, if you're greater than 25 feet, you're tied into this type of an application. So you may not have this option based upon the installation. It's a commercial application like we're seeing on some of this. You're not in that world. So, and then it says condition of maintenance and supervision. You have to make sure that only qualified people are maintaining the system. And it tells you the tap conductors are not over 25 feet long horizontally and not over 100 feet total length. The ampacity of and it talks about the ampacity. It talks about must terminate in a single set, just similar to what we already talked about. It says that you have to protect them from physical damage. They have to be continuous end to end with no splices, and they have to be, the tap conductors are sized a number 6 or 4, aluminum or larger. So you can't have smaller conductors, and they don't penetrate walls, floors, or ceilings. So, and then the last one is the tap is made not less than 30 feet from the floor. So they make you put these tap conductors in a specific location, in a specific type of structure, if you are greater than 25 feet. Now, again, if you're outdoors, no holds barred. You can go as long as you want to go. So, and in fact, the item 5 is outside taps of unlimited length. And there's where the conductors are located outside of a building or structure, except at the point of load termination, and comply with all of the following conditions. There's 4 there, very similar to the transformer secondary conductors that we just talked about, which apply to this application. Located outside of a building or structure, which these tap conductors do. The tap conductors are protected from physical damage, which is true. And really, if you think about the application, these are all outdoors. So we could fall back. I didn't have to worry about the 10-foot rule. I could fall back on the outside taps of unlimited length. These are short, but I could fall back on this if they were longer. They have to be protected from physical damage, which these are. The tap conductors terminate at a single circuit breaker or a single set of fuses, which these do. These fuses are, there's your, right there. So there's your 100 amp fusible switch. The overcurrent device for the tap conductors is an integral part of a disconnecting means. These are an integral part of that disconnecting means. And it's installed at a readily accessible location, complying with one of the following, and it's outside of the building or structure. So just like the transformer secondary conductor requirements, we're outside, and that gives us a lot more freedom than when we're locating these conductors inside. Because remember, these are unprotected conductors at their source. That's a big deal. It's a big deal. From a short circuit protection, from an overload protection, there's an increased hazard because of the location in the circuit and because they're not protected at their ampacity at their source. So we go through all of these special requirements in the tap rules. And understanding the tap rules, I'm telling you that the tap rules can seem confusing. But if you look at your application, read through 240.21 in its entirety to identify which section applies to your application. Once you narrow down the section, the rules are pretty straightforward. The hardest part is identifying the fact that you need to be in that specific location. You know, for the application, you need to be in that specific section within the code. And then you can't forget about the fact that in addition to those secondary conductors, you got to think about the equipment, right? So the conductors, that's the first step. But then you also have to think about protection of the equipment as well, which if you go to 408, I think it is. I always get this section wrong. I think it's 408. Let's take a look. Or is that 406? 408. I'm going to go with 408, and I will be correct. 408, switchboards, switchgear, and panel boards. In addition to the fact, because I get this a lot, well, they'll put a main lug only panel board on the secondary of a transformer. And not only did you violate 240.21 Charlie 1, right, for transformer secondary conductors, which can't be considered protected from the primary unless it's a delta-delta transformer or that single phase 2-wire transformer, okay? And you have to meet the ratios. Not only are you violating that for the conductors, because then they're landing on 6 disconnects or a main lug only panel board, not on an overcurrent protected device. So not only are you not protecting that transformer secondary conductor, but you're also not protecting the panel board. And I'm telling you, this is a highly missed requirement for these applications. So if you go to 408, part 3 covers panel boards. 408.36 is your overcurrent protection for a panel board, and 408.36b is another area that tells you what those main lug only panel boards on secondary transformers are ungood. Is 408.36b says supplied through a transformer. Where a panel board is supplied through a transformer, the overcurrent protection required for that panel board has to be located on the secondary side of the transformer. So putting a panel board on the secondary of a transformer as a main lug only panel violates 240 transformer secondary conductor rules, and it violates 408.36 for overcurrent protection of a panel board. So those are two areas. If you've seen that on drawings, which I know I have, especially in applications where they're trying to meet selective coordination requirements, and any of those overcurrent devices that you can eliminate, the better off you are to achieve the goals of selective coordination. But you're not going to eliminate that main overcurrent protected device on the secondary of a transformer. Regardless, a lot of individuals, a lot of engineers and others will go to Article 450 for transformer protection, and they'll say, hey, Tom, 450.3b tells me, or B for low voltage, A is medium voltage, B is low voltage. They'll tell you that they'll say it says primary protection only. And as long as the thought process is, well, as long as I provide that 125% overcurrent protective device on the primary, then I don't need a secondary overcurrent protective device. But they're forgetting the fact that 450 is about protecting the transformer, not about protecting that secondary panel board or the secondary conductors. 450 overcurrent protection requirement rules in 450.3 are all about transformer protection. And remember, in your typical applications, the primary breaker gives you the primary overcurrent protective device gives you your short circuit protection for the transformer. The secondary overcurrent protective device gives you your overload protection for the transformer. Those are two separate aspects for protection of the transformer, not the secondary overcurrent protected devices and not the secondary panel board that you would be placing on that transformer or any equipment on the transformer. So got to keep that in mind. The scope of the articles defines what the requirements within those articles pertain to. The fact that you have primary only protection at 125% and you don't need secondary protection has zero to do with the secondary transformer conductors or a secondary panel board. It has everything to do with providing protection for the transformer. All right, so hopefully you got something out of this IAEI News Live talk. It's a recorded session. Next week I am traveling. I'll be driving that on Tuesday, so I'll be behind the wheel and I will not be able to go live. So I apologize for that. But I did want to make sure that we continued our discussion on this real world example. And so far we've been through just the general overview, which was 2 weeks ago. This past week, we went over the transformer protection and the rules around selecting the primary and secondary overcurrent protected devices. We did the primary full load amps, secondary full load amps. We selected the primary overcurrent protected device, the secondary overcurrent protected device, and we selected the primary and secondary conductors. Today, we moved over to the transformer secondary conductor protection and the tap conductor rules. So hopefully, we'll continue our journey hopefully next week as well. All right, well, our time together has come to an end. I appreciate if you've made it this far in our 1 hour lunch session of IAEI News Live, then thank you for your attention. And if you've left some comments below, please leave comments. Don't forget to hit the thumbs up. If you hit the thumbs down, you've got to hit it twice. That's just the rules of the road. If you please subscribe, don't forget to subscribe to the IAEI News Live sessions on YouTube. subscribe to the YouTube channel. And don't forget to hit the bell. You'll know when we go live. You'll know when we post videos, and you're just awareness. And it's all free. I mean, that's like icing on the cake for you. So hopefully you've enjoyed our discussion today, and hopefully you've left some comments down below. And if you have questions, please leave those down below as well. If you're looking for additional topics of specific interest, let us know, and we will go find the talent to be able to provide that technical knowledge to you in these 1-hour sessions. And please consider membership to the IAEI. Our existence is dependent upon our members. Our knowledge is dependent upon our members, and our value is our membership. So, and all of the members that you have access to as IAEI members. So please don't forget all that jazz. Take care. Remember to take care, stay safe, and please stay healthy. See you next week.